Alright, so I've just put together a PowerPoint that kind of quickly goes through all the motion revision stuff, and then I'm going to be doing a few examples using the 2012 physics exam, because there's a lot of stuff that's related to the course that's going to be on your SAC that's from there that is, stuff you wouldn't have seen but that will be relevant. So just quickly, the stuff that's going to be on the SAC is mostly, like I've said, in stuff on springs, spring potential energy, spring constants, but you're also going to need to know a bit about kinetic energy and gravitational potential energy and conservation of energy stuff as well. There's not going to be any stuff on like momentum or equations of motion or projectile motion or anything like that. The focus is going to be on stuff to do with springs in particular, but when you get into conservation of energy type situations, then you're also going to need to remember the equations for kinetic energy. I don't think gravitational potential energy is much, but I just threw that one up there, because why not? And also, I started using PowerPoints throughout this term, which I hadn't done with Year 12 physics before, and I'm probably going to just stick with using PowerPoints for the rest of the year. They make it more convenient, and they save time with me writing stuff up. So I guess then the question is, do you write the notes from the PowerPoint, or do you just get the PowerPoint which I upload to Compass? I don't know. Which would you prefer to do? Continue writing notes? Yeah, you can do that. It's just that normally when I make PowerPoints, I normally put in more information than I would if I was to write notes. And so it's like, well, maybe you're writing stuff that you wouldn't normally be writing. I don't know. Yeah, okay. Yeah, I can just upload it to Compass and then you can make your choice about whether you use it or not. But that stuff on the first slide, that's literally all the classical motion stuff that we're going to be doing. So everything except for this stuff is going to be the relativity stuff. So I could have just made the whole SAC about relativity, but I think being able to answer questions about spring constants and that is kind of a key skill you need in physics that you haven't been assessed on yet, so that's why that gets thrown in as well. And then everything from relativity is also going to be on the SAC. So if it's from relativity, it's going to be accessible and it probably will be on the SAC. So you've got Einstein's two postulates that the law of physics are the same in all inertial frames of reference. And if you remember from way back when, if something's an inertial frame, it's not accelerating. It's moving at some constant speed. You've got your different frames of reference, and they're all moving relative to each other. If something's inertial, it's just not an accelerating frame. If it is accelerating, it's non-inertial, and then laws of physics can change from frame to frame. The second one is that the speed of light is the same for all observers, so no matter what your frame of reference is, you're going to see this light moving at a speed of 3 times 10 to the 8 meters per second. So those two things just get called Einstein's two postulates. That's what they are. Looked at the Lorentz factor. I always forget if it's got a T or not. I don't think it does. I'm going to take a moment and just double check. The spelling of it shouldn't really matter, but it matters to me. Does it have a T or not? Let's check it really. Come on. This is useless. I'll figure it out later. And we've got our two main equations. We've got the time dilation and length contraction equations. You just calculate your Lorentz factor. For some reason the gammas come out looking weird in Word, but that's just what that is, the gamma symbol that you use for Lorentz factor. And you remember that when you calculate that, which you're going to be doing in a SAC, it's very easy for things to go incorrect, so you want to make sure that you get a bit of practice at putting this into your calculator if you haven't done it in a while, so that you're not accidentally getting the wrong answer out even though you think you've done it right. Basically, when we're talking about time dilation, we're talking about two frames of reference. One person measures a time within their particular frame of reference, and that gets called the proper time. So if I'm standing in my frame of reference and then you walk past me at some higher speed, the time that I measure within my frame of reference is called the proper time. You moving in your frame of reference would see a different time passing in my frame of reference, and that's what just gets called the measured time, the T. So if it's got a subscript of 0, it means that a measurement is being taken within the same frame of reference as whatever's being, if I'm setting a microwave and I measure 30 seconds on there, that's the proper time. The time that you would measure, it's going to be a longer time because the time's being dilated. You might see that in the time that I measure 30 seconds as passing, that might be like 40 or 50 seconds according to you. So you take your proper time, you multiply that by the Lorentz factor, which depends on how fast the two frames are moving relative to each other. Calculate that, times that by the time. That's going to get how much time is passing in the moving frame. Same thing for length contraction. If I measure a meter in my frame of reference and you're moving past me, then you're going to see that meter as being contracted, as being smaller. You can tell that it's going to be contracted because we're dividing by the Lorentz factor, which is always 1 or bigger. So we're dividing by something bigger than 1, so we're going to get a smaller number as a result. So we take our meter, divide by 2 or something, and we get less length. It's being contracted as a result. And if you remember, I had an example about like a train moving, and we said that if the train's moving horizontally, then it's compressed horizontally, but since it's not moving vertically, it's going to have the same height as it moves. So it gets compressed in the direction of motion, and its height, or whatever is not in the direction of motion, is going to stay the same and not be compressed or contracted. So that was length contraction. We also did some stuff on relativistic momentum. So if this is the classical momentum of something that's moving, and you're measuring that momentum from a different frame of reference, then you're going to see a different momentum. If this is the momentum in the observer's, in someone's frame, in a different frame you would measure just some relativistic momentum as a result. You take the original momentum, multiply it by the Lorentz factor, that's going to get you your momentum in a different frame. And also we said that as an object approaches the speed of light, its mass grows towards infinity. So as something moves faster and faster, it's going to gain mass as a result of that, which means that any force that's acting on it and causing it to accelerate is going to do less and less work. It's going to produce less and less of a change in speed. Since the mass keeps growing towards infinity as the thing approaches the speed of light, ultimately the object never reaches the speed of light because it would take an infinite force to, accelerate it to that point. And the last one's just a bunch of equations about relativistic energy. We said that these are all basically, if you know one of these and you know what it means, then you can basically derive the others. We said that the total energy of something is given by gamma mc squared in a relativistic sense. The total energy can also be considered as the kinetic energy plus the rest energy. Rest energy is just your mc squared. So we looked at questions like you've got, say, 2 atoms that are fusing together. You know the initial mass, you know the final mass. You find that some of that initial mass has gone missing and it has been converted into energy. But if you know how much mass has gone missing, you can take that mass, multiply it by c squared, and that's going to be how much energy is released during that process. Did a couple of questions on that you might want to look at if you've forgotten. And also when we're talking about relativity, we've got relativistic kinetic energy, which we just calculate using Lorentz factor, take away 1, times mc squared. So this equation, you can get it from the other equations if you forget exactly what it is, just because if you take this, put it in there, you take that, put it in there, these two things add up to give you that. So you just got to make sure you're on top of those because they do pop up on the SAC a bit. So what I said I was going to do then was I'm going to the 2012 exam. Grab some pens. I just have to remember not to write on. Actually, I might just lift that up and see if it's going to affect the recording. So I picked the 2012 exam because it's a bit different to how things used to be, but most of the stuff that you're going to be looking at, it's still in the course the way it was back in 2012, and also you're probably never going to go back and look at the 2012 exam, so it's a good resource in that way since it's got questions that are relevant that you'll probably never otherwise see. And that's not rubbing out. So I might make it a bit bigger. So you've got a spring resting against the wall. The spring is compressed by a distance of 8 centimeters, which you'd have to convert into meters if you did any calculations from its uncompressed length. And Jemima holds a block of mass 1.2 kilograms stationary against the compressed spring as shown in figure 1. So you've got a compressed spring, compressed by 8 centimeters, mass of 1.2. She releases the block, it slides to the right on a frictionless surface. It leaves the spring with a kinetic energy of 5.4 joules and slides at constant speed as shown in figure 2. Calculate the speed of the block as it leaves the spring. So you're asked to calculate speed, and it's a spring question, but you're also told that it leaves with a kinetic energy of 5.4 joules. So I'll throw this over to you. What kind of steps would you go through? It's how many points is it? That'll help indicate how much work you need to do. It's a 1-mark question, so normally you'd think that would be a 2-mark question, but maybe they've just changed how they do the mark allocation since 2012. But you're asked to calculate speed when you've got kinetic energy. How are you going to do that? Yeah, that seems fair. You've got your kinetic energy equation, EK equals 0.5 mv squared, and you've just got to rearrange that so you get V equals square root 2EK over m. I'll just rearrange that lots. If you practice this enough, you just know that that's a rearranged equation. And so then it's just a simple, you've got your energy as 5.4, you've got your mass as 1.2. So you just plug that into a calculator and just be careful. Actually, you probably don't need to be that careful with where things go because it'd be hard to stuff this up on the calculator. That comes out as 3. So I'll just double check how I went. Pull up the answers. It says, 84% of people got that right. Speed's going to be 3 meters per second. That's a pretty... It doesn't really have anything to do with springs. It's just a kinetic energy type question. But, yeah, it's going to help if you can do that with the next couple of questions. B was calculate the work done on the spring by the block. So that's another 1-mark question. And it's easier than the first question was. It calculates the work done on the block, on the spring by the block. What is that going to be? It's a very, very easy question in terms of getting the answer to it. You don't have to do any calculations. You just got to read the question and understand what work is. So remember that work is just the change in energy. So it's basically asking, I better just double check what the question says. Calculate the work done on the spring by the block. Yeah. So remember that work is change in energy, right? The spring before it's compressed has no energy stored in it. Once it is compressed, it's got energy stored as elastic potential energy. And then once it's released, all that energy goes to the block. So the block's got 5.4 joules of energy. That means all that energy must have been stored in the spring before the spring was released. So the work done on the block by the spring to give it energy, that's just got to be 5.4 joules. That's how much energy the block is giving to the spring when it's compressed. So that's why it's a 1-mark question. It's just, this is the energy. It's the energy that the block has when it's released. It's the energy that the spring has when it's compressed. That's got to be the work that's getting done in this scenario. So yeah, that's why that's a 1-mark question. Quick and easy. And then you get into question C, which is where it starts being about springs. It says, calculate the spring constant K of the spring. Assume that the spring obeys Hooke's law. So, like I was saying at the start of the lesson, the SAC's going to be about springs, but as part of this you also need to know about conservation of energy and kinetic energy. The reason for that is for a question like this one's 2 marks now, it'd be basically saying that, to solve this, you'd be saying that the kinetic energy of the block when it's moving is the same as the spring potential energy, the elastic potential energy of the spring when it's compressed. So you know that there's 5.4 joules worth of kinetic energy that the block has when it's released. You know that elastic potential energy, that's going to be half K delta X squared. That's your equation for elastic potential energy. And you know that the spring gets compressed by 8 centimeters, so we can write 5.4 equals half times K times point, what's the point? 0.8 squared. It was 8 centimeters, right? Yeah. So that's being converted to meters. And so now you've just got an equation that you've got to rearrange. So you just say that 2 times 5.4 divided by 0.08 squared, that's going to be your spring constant. 2 times 5.4 divided by 0.08 squared should come out to like 1600, I think. Yeah, 1.7 times 10 to the 3 newtons per meter, so about that. Pretty hefty spring. What am I doing here? I don't need compass. So that's how you just work through a question, something like that. And then you get to the last one, which is D, which is calculate the magnitude of the total impulse that the spring gives to the 1.2 kilogram block by the time it leaves the spring. And I guess I don't need to really work through this question because it's about impulse, which isn't going to be on the SAC, but at the same time, I guess this is an opportunity to just revise a concept you need for the exam at the end of the year. So if you remember, impulse is just the change in something's momentum. So we just say the mass times final speed, take away the mass times the initial speed. We know that the final speed came out to like 3, and the initial speed was 0. So you should just be able to do 5.4 times 3, and whatever that comes out as, 16.2. That should be your answer. Unless I've stuffed up somehow. The speed was 3, right? Oh wait, the blocks wasn't 5.4, that was the energy, it was 1.2. That was the mass. Yeah, that one's not quite so crucial, but at the same time, I figure we got an opportunity to revisit the concept from earlier, so why not do so? So that's the 2012 spring question. Now what I'm going to do is jump across to the way... I'm going to show you the year 12 exam, no, the 2012 exam. And it's going to look different to what the modern exams look like, because it used to be the case that you had to do certain areas of study, but then you got a list of like 6 areas of study in your class, just picked one that they did. So relativity used to be an optional area of study, and all the optional ones were just multiple choice questions. The whole section's multiple choice, and that's not the way things are anymore. So these questions, they're pretty tough questions, but at the same time, they're multiple choice, so it kind of balances out. They're hard, but they're multiple choice, so they're a bit easier in that way. So let's work through this. So which of the following factors affects the speed of light? Have a read of those and then, I don't know, vote or something. I'll let you do the reading. So which one do you reckon it is? It's a pretty tricky question, actually. It's not actually D. Because you remember Einstein's postulates, and it says the speed of light is the same for all observers, but when we talk about the speed of light being the same for all observers, we're talking about the speed of light in a vacuum. And we're going to look at this in more detail when we do Unit 4. But you should know from junior science that when you've got light moving through, say, water or something, it's going to bend. And the reason it bends is because the light slows down when it moves through a different medium. So, I don't know, maybe I'm wrong, but I'm guessing A. I'll just C. So yeah, it does seem like a bit of a pain in the ass question where it, yeah. And as you can see, a whole lot of people thought along the same lines you, 72% picked D, but unfortunately the correct answer was A, because they were thinking about relativity when this question also happens to combine stuff about light and its properties when it moves through different media. So, kind of a tricky way to start out the section. See if I can get this whole question. There we go. Is this going to work? Yeah, this one's good. An alarm is sounding in the center of a large indoor basketball court. The stationary player measures the speed of sound at 335 meters per second. The player runs directly towards the alarm 5 meters per second. So you've got your alarm in the middle. The sound's moving at 335 meters per second. This player is running towards that at 5 meters per second. This player is running away at 5 meters per second. And they're both measuring the speed of sound using a small portable device. The question is, which one of these would match with what they measure? So Someone's running away from the alarm, what speed of sound would they measure? Someone's running towards the alarm, what speed of sound would they measure? So this is one of those frames of reference, relative motion type questions. Remember that when you've got light moving through vacuum, it's going to be moving at the same speed for either observer. So if this was light, they'd each measure the same speed. Because this is sound, which doesn't behave relativistically, we've got relative motion, and when these two are moving towards each other, the sound is heading towards this person faster than it would. It's going to get to them quicker because they're moving towards each other. So we're going to have to add together their two speeds, 335 plus 5. That's going to get us our 340. For the person running away, the sound's going to be getting to them at a slower speed because they're moving away from each other. So we're going to have to do a takeaway. So 335, take away the 5, and that's going to be our 330. So just a relative frame of motion type question where two things moving towards each other are going to have higher relative speeds to each other. If they're moving in the same direction, they're going to be lower relative speeds. Aiden? Oh yeah, because running away is this one and running towards is that one. So yeah, it's going to be, I would have said B and would have got it wrong, but yeah, you're right. So yeah, I'm guessing it's D. Yep, D, 68% got that one right. So that's a good frame of reference question. Okay, we've got a quasar, a distant star, is visible to amateur astronomers. When observed, it is at a distance of 2.5 times 10 to the 25 meters from Earth, is traveling away from Earth at a speed of 0.16 c. Which of the following is the best statement about the light from the quasar? Light from the quasar will traveling slower than light shows Earth. Light from the quasar will traveling faster. Yeah. So it's the downside of having these multiple choice questions. Some of the wordings get kind of detailed, but I feel like you can straight away eliminate A and B, right? It's talking about light moving faster or slower when it's moving through vacuum, and you know that's not going to be the case. So you can pretty much just knock these two out straight away. The light from the quasar has taken that many years to reach Earth, and light from the quasar has not yet had time to reach Earth. Not yet had time to reach Earth. Instinctively, I want to say that D has to be wrong because hasn't had time to reach Earth. What are they talking about? So I'm guessing you just do a calculation of, this isn't so much relativity as it's just basic motion, but question like this, if you want to check whether C is correct or not, the time that's going to take to reach Earth is going to be the distance that it travels divided by the speed that it's moving at. I'm guessing we can just use this classical equation of motion because we've got a pretty low speed. The distance is 2.5 times 10 to the 25. The speed is going to be 0.16 times 3 times 10 to the 8. If you put that in the calculator and it comes out as 2.6 times 10 to the 9, then the answer would be C, which, hey, it happens to be C for that one. So I'm guessing that's what it comes out to. I'll save some time and not put it into a calculator because that seems like the only one that would be right. I think there's like 12 questions and now they're all yellow. So yeah, I might just go through all of them as a bit of revision. One of Einstein's postulates for special relativity was that the laws of physics are the same in all inertial reference frames. Which of the following best describes the property of an inertial reference frame? I'll let you have a read and then tell me which one you reckon it is. So which one do you reckon it is? B? Seems fair. If they're not accelerating, then they're in an inertial reference frame. Yeah. Stop doing that. That's probably unpleasant for people watching at home. It keeps going yellow. Now it's just staying yellow, so that's not fun. So you can straight away figure out that A, it's got nothing to do with anything that we've talked about, and so it's probably not going to be right. C, that's not what an inertial reference frame is. With question D, that's actually a tempting one to pick because if it's moving in a straight line, then actually that's not a tempting. It could be accelerating in a straight line, so that's a crap answer as well. Yeah, it's got to be B. Otherwise, that doesn't make much sense. Yeah, 73% pick B. Next one, 90% have got. Actually, we'll skip question 5. It's about the Michelson-Morley experiment, which is something that no longer gets assessed on. So we'll just pass over that and do question 6, even though it's apparently a pretty easy question. Rest mass of every proton is 1.67 times 10 to the negative 27 kilos. One proton has a kinetic energy of that. Which of the following is the best energy of its total estimate of its total energy? So it's asking about total energy. I had up the equations before for relativistic energy, and the equation for total energy was E total equals gamma mc squared. So you've just got to calculate your Lorentz factor, which actually doesn't give you the speed. No, my brain's having the... Oh wait, no. I'm going to have to do this a different way. Because it doesn't give you the speed, then you're going to have a hard time calculating the Lorentz factor, and because this is relativity, you can't go straight from kinetic energy to that. So I'd say that, what am I going to say? E total equals E kinetic plus E rest. Kinetic energy is 9 times 10 to the negative 11 joules, so that one's straight away given to you, plus mc squared. So 9 times 10 to the negative 11 plus 1.67 times 10 to the negative 27 times 3 times 10 to the 8 squared. And rather than waste time and calculate that, I can just feel confident that that's the way you do it. So you just have to pick the right equation, go with this one. If they'd given you the speed, then you could have calculated the Lorentz factor and done it the first way that I was going to do, but since they haven't given you that information, you kind of got to use a different equation to get that done. Question 7, the particle is travelling at a speed of 1.47 times 10 to the 8 meters per second. If the speed is doubled to 2.8 times 10 to the 8, 2.8 times 10 to the 8 meters, which of the following is the best estimate of the ratio? The Lorentz factor when it's moving at this speed divided by the Lorentz factor when it's moving at that speed. And I'm sure there's a very clever way to do it fast and quick. The short way, the reliable way of doing it is that the Lorentz factor at speed 1 is just going to be this divided by 1.4 divided by 3 squared. The Lorentz factor at the highest speed is just going to be 1 divided by 1 minus 2.8 over 3 squared. And you can just figure out what each of these are and then do this one divided by that one, and I think it comes out to B for 2. So you don't really need to do any fancy algebra for that one, although I'm guessing if you do that, it might be a bit quicker. Question 8. Which of the following statements about the proper time between two events is most accurate? So I get you to read that one. It kind of goes over what I was talking about before, but it's wordy and I don't want to read it all out aloud, so I'll let you spend 30 seconds thinking about that one. It's probably pretty hard to read for Scarlett. I better figure out what it is as well. Alright, so what do people think it is? I'll give you a cheating hint and say it's kind of got to be A or B, right? Like either the time measured in a different frame is shorter or the time measured in a different frame is longer, because we know about time dilation. And so you can automatically say, well, if one of them has got to be correct, then it's probably not going to be C or D. We know that time dilation is that if you have a proper time measurement, then our equation is T equals, dilation means bigger. So this is our time dilation equation. This is the proper time. We're multiplying it by the Lorentz factor. So in a different frame of reference, we're always going to get a larger time. So I reckon it's got to be B. Question 8. Is it B? Question 8's A. Okay, now I'm confused. Oh yeah, that's right. Oh yeah, because, yeah, so it's talking about the measurement in a different frame, which is this one, and the proper time is, like Aiden's saying, this divided by that, and so, yeah, it's just worded backwards to what I thought it was, and so I was wrong. Questions 9 and 10, spaceship A is a circular window. I'm just going to rub this out while I rejig my brain. Spaceship A has a circular window on the side. Alan, a crew member of Spaceship A, measures the diameter of the window as 20 meters. Figure 2 shows the Spaceship A at rest. Someone is in a different spaceship, measures the dimension of the window, moves past at a certain speed. It's probably going to say, how big's the window? That's the problem with the question. Yeah, that's a good question, actually. So the window was 20 meters in diameter originally, and then Spaceship B is going past and sees Spaceship A, and the window on Spaceship A, and it's asking what would the person on Spaceship B see the window as looking like. So which one's it going to be? It's a good conceptual question. Yeah, it's going to be D. They're moving sideways, so it's going to be contracted, the length's going to be compressed horizontally. It's not going to be compressed vertically, so it's going to remain the same height, 20 meters as it was. So it's got to be compressed horizontally and the same vertically, and that's the only one that's going to match up with. So, yeah, D is going to be it, I assume, unless I'm wrong. Yep, it's going to be D. Got a couple more of these, and then I'll let you go on with your revision. Bryony on special. I might pass that one, actually. Not so relevant. Yeah, that one's kind of crap as well. Yeah, and question 12, the last one, that's not bad, it's a tricky one, but it says a helium ion is accelerated from a speed of that to a speed of this. Scientists calculate accurately the work done on the helium ion during this acceleration. You've got your data, its mass, its rest energy, and its Lorentz factors. Hey, they give you most of the stuff you need. Which of the best options below is the best estimate of the answer they obtained from that? So you're talking about, again, what is the work done? Those are the big bold words that you're looking for. Work done, again, that's just the change in something's energy. So we're looking at how the energy of the object is going to change. And the rest mass and the rest energy, they're not going to change. All that's going to change as it accelerates is its kinetic energy. Relativistic kinetic energy is this equation. So you basically find the kinetic energy at time 1 using this speed here and this Lorentz factor here. Then you find the kinetic energy at time 2. Same thing, same equation, but the Lorentz factor is different now. So you just say this one's going to be, you can actually do this pretty easily. 1.05 take away 1 times the mass times c squared, and this one's going to be 1.15 take away 1 times the mass times c squared. Wouldn't take long to calculate actually, but I'll pass up on it. And then I'm guessing you do this one, take away that one, and it's going to come out as one of these answers. I think that's, yeah, going to work. But I can check later on maybe. So that was the end of, I think, yeah, the 2012 relativity multiple choice questions, and it covers most of the stuff that you're going to need to know. So, yeah, I think in a previous lesson I said specifically what the revision questions were, but maybe I'll write them up again. I'll just have to check what they are. And I guess we're sticking with the time frame that we'll be having this SAC next Friday. So, yeah, if you want 3 lessons of revision, if you come in after 2 lessons of revision and you just want to move on to a new topic because you don't feel you need another lesson of revision, we can do that. But otherwise, yeah, I guess the plan is 3 lessons of revision. So let's see, the questions were, where were they? There was chapter 6, I want to say. Chapter 7 maybe? Chapter 6 was special. It was actually. So yeah, everything from chapter 6 is relevant. So you might just want to do the review questions at the end of chapter 6 for that. There's 20 of them. And also the spring stuff, which is, it's got to be chapter 7. Hold on. I should have planned this. Yeah. Pretty much all of chapter 7 actually, so except the stuff on like areas under graph and that sort of stuff, which we might want to do for the SAC as well. So yeah, chapter 6 and chapter 7, the review questions from there, those are the things that you should be looking at for the class. I'll stop the video.